directed. There we go. Which I'll be choosing to be past directed rather than Peiken's future directed. But apart from that, same notation. And we introduced this frame field that we can choose on our initial two-sphere that we can Lie drag all the way along the null hypersurface. And we showed that that frame will remain tangent to the leaves of the foliation. And we can use that to propagate all kinds of geometric quantities, the metric along the flow, as well as the second fundamental form for the leaves along this L-bar direction. And then we finished up last time, proving by the definitions that I threw at you for a null cone that we conclude that the trace of this chi-bar is always positive. Or you can think of that as the mean curvature vector for your two-sphere in the direction of L-bar, or with the inner product with L-bar, right? So trace chi-bar is exactly the mean curvature inner product L-bar with that minus. And we showed that must stay positive. So today, what I'd like to do is, after all that pain and suffering to put the framework together, let's look at some examples. So I'll give you the most general example of a null cone of Minkowski, and then of course, the most important one for us is going to be the null cone of a point. And that I'll use to complete an argument, or just to push further an argument that Mutau showed us last week, Tuesday, relating to round metrics, to motivate the idea of mass of a null hypersurface. And rather than me giving you all the horrible definitions of the decay conditions we need for omega to define mass, I'll just heavily lean on the Schwarzschild geometry to motivate that, and then we can prove what I wanted to prove, which is the null-Penrose inequality, after, of course, defining precisely what the null-Penrose inequality is, finally, for null cones in vacuum that are shear-free. Okay, and for me, shear-free just means the traceless part of chi-bar vanishes. All right, so one important thing that we get from trace chi-bar being positive is I can choose a gauge-independent null frame for my leaves. What is that? That just means I can take my L-bar and I can now divide it by trace chi-bar. And notice for any gauge change, i.e. a multiplication of L-bar by some positive function, which of course enforces division of that function by my previous L in order to maintain my convention that the inner product remains 2, taking that ratio with the new tangent vector gives me exactly the same L minus, and that's why I call it gauge independent. Okay, so I'm not going to lean on this basis right away, so it's kind of silly that I introduce it right now, but I'm going to use it later. So to save some time, there it is, and we can define this gauge independent L minus L plus. And remember, we had a torsion tensor coming from L bar L. We have the corresponding torsion tau now. Okay, so that's how it would be related to the previous choice of gauge, but we can define a tau. And what's interesting about this choice of gauge as well is if I now look at what was previously chi-bar, this 2 tensor now becomes a trace equal to 1. And if we look at the trace of what was chi before, but what is chi plus now, you see that it gives us exactly the inner product of the mean curvature with itself on that 2-sphere. Okay, so I'm going to come back to this basis a little later. Now, rather than me, let's see here. Yeah, right here. So, okay, as promised, let's go into null cones of Minkowski. All right, so the null cones. Now, my notation is a little bit weird just because I learned differential geometry from a slightly unconventional book, but it's R4, right? But rather than R3 plus 1, you put the 1 just down here because it identifies the signature. So, sorry for being contrary to the convention, but R41 from now on is just Minkowski space. So just a quick reminder, it means I've got a nice R4 with a metric eta, where we know and love eta. And later on, if I use subindices I, like partial sub I, it just means I'm running through X, Y, and Z. Okay, and the context will be clear that I'm not confusing with my lead dragged frame. Okay, so this is Minkowski space for us. So take any 2-sphere then in Minkowski. At least for a small affine parameter, we definitely know that I will be able to shoot geodesics off of it. Okay, and I'm going to assume that this is of course, a two-sphere. And now let's just take three derivatives of the metric that I get when shooting along those geodesics. Okay, so without loss of generality, as I said last time, why not just take geodesic null vector fields normal to sigma? And from our propagation equations, one derivative, remember, tells me that this is twice chi bar. All right, now I take another derivative. Let's pull out that 2. What do we end up with? Well, if I take the derivative of chi bar and I'm in Minkowski and I'm assuming geodesics, this is just simply chi bar ik, chi bar kj, and I've still got one derivative to go. Well, but this is also easy. Remember, this is simply some raised metric to give me the upper k, L, J. And now just taking a derivative of those three tensors, you'll see something nice happening here. And that's why I've taken three derivatives. Oof. All right, so notice that when we take the derivative of the inverse metric, we get negative 2 chi kl. We have the ik, the lj left alone. And then I'm going to hit chi bar with that derivative, but I'm going to hit it twice. And because of the symmetries of chi bar, this will just be a plus 2 gamma kl. And then what do we get for the derivative? Well, we remember that's going to be chi bar I n n k, and then I have to hit chi bar l j. All right, and what do you notice here? This is exactly equal to 0. All right, so what's really nice in Minkowski is if you just incorporate then the initial conditions, you see immediately that your metric has to be of the form, whatever the metric was on sigma, the guy you started from, the two-sphere you started from, and then you have the initial chi bar that you started from, and you have to square this. All right? And here, what do I mean by square? This is with respect to gamma 0. Okay, so you take this metric, you raise the right index by gamma 0, and then hit it with itself again. So the metric takes a very nice form if we're in Minkowski space. And if I'm going to be talking about a null hypersurface, a null cone, excuse me, then I'm going to be assuming I can keep flowing along L bar indefinitely. So rather than going through the details, you can probably see that it's clear that I'm going to be able to wedge between whatever my sigma was and the infinite flow to the past. I'm going to be able to wedge in some space-like hypersurface. Space-like hyperplane. All right? And it's going to be diffeomorphic to an S2. So why is that useful? Well, rather than me talking about gamma 0 and chi bar 0, because I can wedge in a hyperplane in between my initial surface and null infinity, let's just, without loss of generality, imagine that I've constructed this null cone from that wedge instead. Okay? So why do I do that? Well, now I can express the geometry, at least with regards to my initial sigma, as the data on a two-sphere embedding in an R3. Sorry.
In the beginning, we assume half equals 0.
Say that again?
The initial half of k equals 0.
Oh, do you remember? So at the very first board, I had dl bar L bar equals kappa L bar. So that's just, you can...
You can say
No. I have the freedom to choose it to be 0. Just scale it so that it's affine. Yeah. So kappa, this is, this k is supposed to be a kappa, but I can't draw kappa, sorry, yeah.
in Minkowski, if
Null infinity, no.
Without any attraction.
No, I'm assuming, so I would like to give you the examples of null cones in Minkowski. So let's assume that I've got a null cone coming from this sigma, and then I'll tell you what sigma has to satisfy for it to extend to infinity. So yeah, I'm trying to characterize what null cones are in Minkowski. Okay, so if I have a null cone, I can wedge a hyperplane in between it and null infinity, which means that I can rewrite, okay, so without loss of generality, let the sigma that I've constructed the null cone from be equal to the intersection with that hyperplane. Okay, so without loss of generality, let me just construct it from that sigma instead. Okay, so maybe I should call this sigma original, and then why not just go and use that sigma to talk about this null cone instead? All right, now notice what that means then for the metric at least. It means that the metric is now exactly gamma 0 minus the second fundamental form of sigma, where this guy is the second fundamental form when we think of this sigma now as being embedded into R3, all right? Because it's a space-like hyperplane, it's isometric to R3. All right, so let me show you what type of surfaces sigma can be by using the geometry of sigma when you think of it as an embedding in R3. All right, so what we can do then is rewrite this as 1 plus, now if I remove the trace out of my second fundamental form, then that's going to produce an HS over 2 along the metric, and I'm left then with the trace-free part, right? So just remembering what the trace-free part is from last time, you subtract off the component along gamma 0.
So what is the, you're assuming the sigma is intersection, so you assume it's a surface in R3.
Yeah.
What is this gamma 0 here?
It's just the metric on sigma.
It's different from that gamma, right?
Yeah, I've reorganized my whole, I've reorganized myself so that gamma is now just this.
You get a new surface in R3.
That's right.
And that's your gamma 0.
Yeah, so what I've just said before is, remember, we can do all of this. I can wedge in a hyperplane. So let me just reimagine that I started from that intersection. So without loss of generality, to describe my null hypersurface, let sigma be the intersection with this hyperplane.
But this gamma 0 is different from that one, right?
Yes and no, if you just think of it as I was going to choose this one from the beginning, yeah. It's the same gamma. This is, if I choose an initial surface, this is the metric on it, correct? Right?
No, I'm confused.
If I choose an initial sigma in Minkowski space, this is the metric that it has along the flow. So now just choose that initial surface to be the intersection with the hyperplane. Then gamma 0 is just the metric on this surface, and it's the metric on it.
On this one?
On the sigma.
But that's gamma, right?
That's gamma.
What do you have a gamma 0?
Oh, gamma is the foliation along the null hypersurface. Yeah, so it introduces a flow along the affine parameter called sigma s.
What is that gamma over here? Gamma is equal to gamma 0 minus s sigma. Okay, that's another s.
Sorry, yeah.
That's different part. Okay.
Yeah, sorry. Thank you. Yeah. All of that confusion was because I forgot the s, yeah.
And what do you have? What do you put an s? What do you put a minus sign in s over there?
Oh, because if you look at the definition of chi-bar, it's actually minus the second fundamental form. It just depends on your convention.
So that chi, we should really think of that chi as a chi 0 bar, a substitute for that.
Yes, and because it's a hyperplane, t is perpendicular, so the only thing that survives is the normal vector, so it's just the second fundamental form of sigma in the hyperplane.
But what you're secretly identifying this second polynomial with a chi bar.
Yes, on the initial surface. On the initial surface, yeah. That's exactly right. Thanks for the question.
So what condition do you put on sigma after 0 to ensure that it lies on the second?
that's coming. That's exactly what I'm trying to get to, yeah. That's what I'm trying to get to, yeah. So if we assume that we have a null hypersurface and we identify these metrics, you can write it in this form. So I'm going to identify the condition with the mean curvature and the Gauss curvature of that embedding. Okay, so if we assume the null cone remains smooth, this is the induced metric of the leaves off of the initial embedding in R3. And now I'll leave it as an exercise, but if you calculate this quantity, you actually get the following. Sorry, does that make sense now? All right, so if we take this determinant, you'll see.
I mean, your H and the trace-free second one, the one part, they're totally independent of S.
Yes,
Yeah.
that's right. Yeah, this is, well, I mean, this is chi bar. Yes, it's not chi bar, but it was S chi bar 0.
Yeah.
But I can think of that as the second fundamental form.
It's just when you write it, for example, the line over there, your gamma actually depends on S, but your
Yes.
gamma 0 and second fundamental form are independent
Of S, that's right. Yeah, so you should think of this as the initial, and gamma 0 is the initial. So if you calculate the determinant of this quantity, you'll see that it's 1 plus hs over 2 squared minus, and you get a half s squared, and the norm in gamma 0 of the trace-free part squared, that gamma 0. Okay, so just calculating this quantity. Okay, so one of these that I'm squaring, I'm just calculating the determinant of it. And this is equal to, if you combine powers of s, this is h squared over 4 minus 1 half the trace-free part squared s squared plus hs plus 1, that gamma 0. And recognize what this is. If you think of sigma as an embedding in R3, this is exactly the Gauss curvature times s squared plus hs plus 1 times that gamma 0. Okay? So, what we can see then is if I'm on a null cone, then trace chi bar has to be positive, and that will enforce conditions on k and h. And you can show that when you put those conditions on k and h, you will also be able to generate a null cone. Okay, so here k is Gauss curvature. If you think of sigma as an embedding into R3. All right, so remember, if we have a null cone, this guy has to be positive. All right, and remember from last time, you can get trace of chi bar as the derivative of the determinant of gamma s along leaves of your flow over 2 times det gamma s. And for us, just the calculation will show, because of the determinant of this quantity being equal to this, is exactly 2 Gauss curvature s plus h over ks squared plus hs plus 1. If it's a null cone, this must be positive. So what you see from that, just by varying your values of s, is therefore, if you assume it's a null cone, h must be positive and Gauss curvature must be non-negative, i.e., the sigma that produces a null cone is convex. Okay? So if you assume a null cone, you can wedge a hyperplane between, you can take an intersection with a hyperplane. If you study the cross-section that you get, you'll get a cross-section with positive mean curvature, non-negative Gauss curvature, so it must be convex and vice versa. I won't go through the details. You can show if you start from a convex surface in a hyperplane, shoot GD6 off of it, that's going to give you a null cone.
Your null cone is actually just a null hypersurface.
Yes, yes. Well, with those conditions.
Coming out from the point.
No, not necessarily coming
You
from.
said all the way to infinity.
That's right. So those are the assumptions. The definition that I gave last time, sorry, I should have maybe put it back up, will force the cross-sections with these hyperplanes to be convex two-spheres. And vice versa. If you have a convex two-sphere, it will produce that null cone that I gave, the definition that I gave last time. Okay, so that's what null cones are then in Minkowski. So there's, of course, a very special kind that I would like to borrow to motivate mass. And that's, of course, when it does come from a point. Okay, so there's a special case. What happens if I'm looking at one of these cross-sections with Gauss curvature being exactly 1/4 h squared? Well, we know, of course, that forces both k and h to be constant. And then the null hypersurface that results, I'll give it a new symbol, lambda. And lambda is given by the following. It's all points in Minkowski. And I would like to characterize it with the position vector. If you take the inner product, so you choose an origin for Minkowski space, right? And then if you look at the null cone to the past of the origin, then the points on the null cone are characterized by the inner product of this position vector being equal to 0 when inner product with itself. And what is the position vector? It's just t dt plus xi di, and here I just mean x, y, and z. Okay? So we know and love this guy. It's just all vectors pointing out of the origin with null causality. So we've got our t, our x. Let's suppress y and z, and then what this is drawing out for us is just the null cone to the past. Okay, so any point has the position vector pointing along that direction being null. And then we get a null cone of a point. All right, so this is going to be an important characterization, but I'm also going to borrow Moutel's change of coordinates. So recall, we can also write dt squared plus dx squared plus dy squared in polar coordinates on our way to choosing a null coordinate. So let me just use this opportunity to use my notation for around S2. All right, so if we let V be equal to T plus R, then we can also change this to negative dV squared plus 2 dV dr plus R squared d sigma squared. And we recognize that the null cone is therefore a level set of this coordinate V. Okay, so this allows us to write this guy as the level set V equals to 0. Now, last time, when we had a null hypersurface described as the level set of a function in general, I gave you the identity that taking the gradient of this V, taking the covariant derivative grad V, this is exactly 1/2 the gradient of grad V squared. But because grad V gives null hypersurfaces as a constant, when you fix V, you get null hypersurfaces. We saw this forces grad V squared to be 0, at least on omega, right? But here, because it's a coordinate, this is actually true wherever V is defined. Okay, so this is actually true on all of R41. So the point I'm trying to make here is I can now take the gradient of something that's always 0, and this is equal to 0. So it's now true geodesic vector field tangent to the null hypersurface, and that also just re-justifies why Mutau said that this partial r in the coordinate system that I've given you, v r theta phi, partial r is actually geodesic. All right, so that is now tangent and geodesic to the null cone. So the point is, I can describe any cross-section inside of the null cone of a point by just specifying the radial coordinate as a graph over S2, i.e. just give r a function in theta and phi, and that will uniquely characterize all cross-sections of the null cone. All right, so for any sigma in the null cone, sigma can just be given as some function then, where r is some function of theta and phi. All right, so
What is this? Any space-like surface?
for any, yeah, this is space-like. So yeah, for me, sigma will always be a space-like two-sphere, a Riemannian two-sphere. All right. So I would like to talk about constant Gauss curvature cross-sections of the null cone of a point. All right, so last time Mutau showed that there are certain cross-sections then, by choosing this function in a special way, you will actually produce Gauss curvature equal to 1 cross-sections. And I would like to prove that those were actually all of them. So just a quick reminder, maybe I'll switch board because I'm going to start hiding behind the podium. All right, so remember, any isometry of Minkowski will be called a Lorentz transformation if it keeps the null cone invariant. All right, so let me ignore rotations. So if we ignore the rotations, all that's left are the Lorentz boosts. And these are given by, if I give you a t and I give you a r coordinate, I'll write it as x, y, z. Okay, so I have a radius r and I'm pointing in some theta phi direction in R3. That gives me my R3 coordinates. Then the Lorentz boost takes us from this vector to gamma t plus rv dot n and stuff that I can give you, but it's not going to be too helpful for us. All right. So, just to recap quickly, because I think Mutau gave most of the argument already. So,
What is gamma?
I'm going to give it, yeah, so where n theta phi is just a unit position vector. In R3. V here is just some vector in R3 in the unit ball. And gamma is 1 over the square root of 1 minus v squared. All right? So v is just an element in the unit ball. So something in R3 with length less than 1. Strictly less than 1. Ooh, I'm using my... I'm running too big here. Maybe I'll cut the board in half. That's right. So if we if we take a cross-section of the null cone, it means that t plus r has to be 0, right? And I can uniquely express it as some function omega. And under a Lorentz transformation, if I choose such a transformation that brings me to -1 in the t-coordinate, I must have some unit vector. It's not necessarily, of course, going to be the original. All right? So let's say under some choice of v, I perform a Lorentz boost, and it takes me to -1 and some unit vector in R3. Then what that forces by that formula, as we saw last week, is that omega must be of the form 1 minus v squared, 1 minus v inner product n theta phi. All right? Because this, if you plug this in for these coordinates, that's what's going to take you over here to -1. All right? So that means for these cross sections identified by v, we must have, because it was an isometry from whence it came, that these must be equal to 1. All right? Because the Lorentz boost is an isometry. So Gauss curvature is invariant. It ended up being 1, so it must have been 1 originally. Okay, so this is just a quick rerun from what Muta said last week. So what I would like to quickly prove... Yes, yes, of course, yeah, I'm using the path. So what I would like to do is I would actually like to show that if we have any cross-section of the null cone and we see that the Gauss curvature is constant, then it means that I can describe it as a graph with function exactly what we had before, just scaled appropriately. Because these are going to give us a big hint on what to think of as mass later on. Okay, so if I have a cross-section in the path null cone and I have constant Gauss curvature, it means that I am a graph of this form. Okay, so why is that the case? All right, now because the Lorentz boost is linear, all right, so because I know that all of these graphs came from intersections with hyperplanes, right? Because I can get each one of these functions just by the appropriate boost to the appropriate hyperplane. Okay, so Lorentz boosts are linear. It implies that sigma given by omega v for some omega v must be the intersection of the null cone with some hyperplane E. In fact, it's going to be the hyperplane that's got normal tangent vector gamma 1 v. All right, so we know that all of these functions come from intersections with hyperplanes, so it suffices to prove, and I'm just going to go for k equals to 1. You can just get all of the constant k's by a rescaling. So it suffices to prove that when k is equal to 1, we have that the sigma with constant Gauss curvature equal to 1 is in some hyperplane. Okay, so what I'll do is I'll assume k is equal to 1 and then prove that the sigma must be an intersection with a hyperplane. And that exhausts then all constant curvature k's, right? Because we know that all of the constant curvature, all the hyperplane intersections are described with this omega. And it's a neat little proof that I wanted to share. So it basically just leans on the Gauss and Kadazi equation. So the Gauss equation tells us, remember from the definition last time, is that K is 1/4 H inner product H in Minkowski. All the other terms are 0. Okay, now I'm assuming that K is equal to 1. So let's choose a unit normal, nu, which is just 1/2 the mean curvature. Okay. Now, we have another normal vector to sigma, and that's namely the position vector restricted to sigma. Okay, so since P is null, all right, P is the position vector, we have a basis nu and P for the normal bundle. Okay, so I've got my two normal basis vector for the normal bundle. So
How do we know they're independent?
this one's space-like, this one's null. So they have to be independent, that's right. Okay, so quick observation. What's nice about this position vector is if you take the covariant derivative with any vector, it's going to just pop back x. All right, and that's just because P is this is the coordinate vector, so when you take a covariant derivative, all you're pulling out here are the components and then matching them with the partials. So this is true for any x in R41. Okay, so what that means then is the inner product between these two normal vectors, v and p. Well, remember what this is. This is 1/2 the mean curvature. So I can do a little flipping the covariant derivative from one side to the next. And you get, so let's choose just the frame. Right, remember mean curvature is the trace of dxi dxj, so I can pull that over to the right-hand side because this is tangent, and that is normal, and then I introduce a negative sign in the process. But this is just xj, so this is exactly -1. All right, because it's the trace of the metric. dxjp is just xj, take a trace, you get -2. You get 2, divided by -1, you get -1. So what's the significance of this? Well, notice then that the normal component let's see here. So this is equal to -1. So what this allows me then to do is to take a derivative then. So from now on, let v and w just be some tangent vectors to my sigma. Then if I take a derivative of -1, I get 0, of course. This is going to be dv perp of nu p. And then it hits the p, but that just gives me v back. Remember, that's nice property. So this is exactly d perp v of nu p. So what we see then is we get 0 when you take tangent derivatives of this unit space like normal, and therefore it must be identically equal to 0. Okay? Of course, the component of this covariant derivative along nu is 0 because it's a unit vector. All right, so that's the first thing we're going to need to show that sigma is contained in a hyperplane. All right, so the normal component is 0. Because it's a basis, we can write the second fundamental form as some symmetric 2 tensor alpha times the direction p plus some symmetric 2 tensor beta times the direction nu. All right, and I can show that beta is exactly the metric. So why is that? Well, I get hold of negative beta just by taking an inner product of the second fundamental form with p. Because p hits the second fundamental form, it hits this to give me 0, hits this to give me negative p. So this is exactly equal to this. And by flipping the covariant derivative in the second fundamental form, this is exactly dv pw. And remember, that's exactly VW. So beta is just a multiple of the metric. Gamma. And notice then, if I take a trace, then the mean curvature is equal to trace alpha p plus the mean curvature h again. So this means that trace of alpha must be 0. So alpha must be equal to a trace-free 2 tensor. Okay? And now we've exhausted the Kadazi equation. And we move on to the, we've exhausted the Gauss equation, and we're going to move on to the Kadazi to give us the last little bit of information. Okay, so secondly, now we move on to Kadazi. And what is Kadazi? Now, last time I gave you the trace of the Kadazi, but in Minkowski, in full generality, the Kadazi equation is just the statement that if I take v, w, u as tangent vectors, I look at the normal component of the derivative, then I can flip v and w. All right, so that's just the statement for a codimension 2 surface in Minkowski, the Kadazi equation in Minkowski. So I'll leave it as an exercise, but it's a really easy consequence then of the fact that beta is gamma and that the perp of nu is identically equal to 0, that this directly translates into the equation. If I look at the covariant derivative along sigma, you just basically translate that property onto alpha hat. So notice now what happens if I take a trace over v and u. I get, so just trace v and u, then what we see is the divergence then of alpha hat, and you plug in w, is exactly equal to w, the trace of alpha hat, which we know is of course 0. And that forces the divergence of a trace-free 2 tensor on S2 to be 0. But we know this is injective on traceless 2 tensors that are symmetric. So that means alpha hat must be 0, and the second fundamental form then is exactly a multiple of the metric. All right? So what do we see then? This means the second fundamental form is exactly equal to gamma nu. All right? So why is that interesting? Well, now we can get more information about the covariant derivative of nu. We know this in the perpendicular direction is identically 0. So we can uniquely characterize it by looking at what this quantity is along tangent v and tangent w. But that's exactly negative nu, the second fundamental form, which we now know is just gamma times nu. So this is just minus vw. So we conclude then that covariant derivatives along this unit normal is exactly the negative of the tangent that you put in. And we're done, because now construct for yourself a unit time-like normal vector field just by adding nu to P. To sigma. All right, just take an inner product with itself, you'll see that you get -1. And this means, well, if I take now a covariant derivative, what did we see this is equal to? It's negative v plus v equals to 0. So what we see then is that this choice of unit time-like is constant. And that means it must be contained inside of a hyperplane. Okay, so this shows us then that solutions to the Gauss curvature by a conformal rescaling that's constant must come from these omega v's, and they are the only ones. All right? So there you go. So that means I can uniquely characterize constant Gauss curvature cross-sections in the null cone of a point, and this allows us to say some interesting things about mass, and to do so, let me go to Schwarzschild. So maybe a new board. All right, so mass of omega, and I'm going to be leaning on Schwarzschild. So remember, what's the Schwarzschild spacetime? Well, the metric is negative dt squared with a factor of 1 minus 2m over r, as we've seen now multiple times, plus dr squared 1 minus 2m over r, plus r squared d sigma squared. And I can make a similar change as we saw in Peikan's lecture with choosing my v to be, no, this is what you would do in Minkowski. This is what you would do in Schwarzschild. And this change of vector gives us then the metric dv squared plus 2 dv dr plus r squared d sigma squared.
dv is equal to dt.
Partial. Yes, thank you. Sorry. Yes. Yeah, not t plus r. Thank you. Yeah, that's me trying to go too fast. So this is dt dv is equal to dt plus that. All right, so notice once again I've introduced a coordinate vector v that if I look at its level sets, I've got a degenerate metric. You can check once again, therefore, that grad v must be a null geodesic vector field, and it's exactly partial r. All right, for the same reason as Minkowski. So the picture that we've got now, notice here that as r goes to 0, we've got a blow up in that first component. So I've got now a singularity at r equals to 0, and then a null hypersurface coming out of it. Let me go back to omega. And the exact same arguments go as before. If I look at any cross-section, I can just characterize it as some graph over a two-sphere. But we can say more. Notice if I put v equals to a constant, the only thing that survives is that. That is exactly the metric of the null cone of a point in Minkowski. So from the point of view of intrinsic geometry, this is indistinguishable from a null cone of a point in Minkowski. So the argument I just gave for finding constant Gauss curvature cross-sections is exactly the same here. All right? So in fact, if you look at the metric on these null cones, given by v equals to some constant, it's exactly equal to r squared d sigma squared, and this is precisely the metric of a null cone of a point. So we can conclude that k is going to be 1 over r0 squared if and only if the graph omega theta phi is of the form r0 1 minus v squared 1 minus v n. Okay, so why do I care? Well, no, but the geometry is the exact same. You can do all of the arguments we gave previously the exact same way. And it all comes down from the fact that the metric there is the same, which means that the chi-bar is going to be the same. Everything that we've used we'll go through. So how does this...
But you don't really have the Lorentz group acting on the function.
No, you don't, but I'm just simply saying here, if I want to find cross-sections with constant Gauss curvature, that's the graph function. So just hold on to that truth. And I want to use that to motivate an energy. Okay, so All right, so what is this energy I speak of? So you may have heard of the Hawking energy. So let me see.
It's a wrong call.
Yes, yeah,
Yeah, and you have a cross section.
that's right.
The Gauss curvature is
Constant if it looks like that. All right, so exactly right. So let's move towards the energy and mass of omega. So definition. So I'm going to throw an energy at you, and then I want to justify why we call it an energy. And it's going to be given for a space-like 2 surface sigma, as always. And the formula for this Hawking energy is the square root of the area of sigma over 16 pi, and then you integrate the Gauss curvature minus 1/4 h inner product h. Okay, so why is this an energy? Well, let's look at, I guess I can keep the picture. So I guess I'll leave this again as another exercise, but if you study the Gauss equation in Schwarzschild for cross-sections of this null hypersurface, you observe now, remember in Minkowski we had k equals 1/4 h inner product h. Here we get, rather than this being equal to 0, you get, interestingly, that this is exactly 2m over omega cubed. All right, so this is some multiple of the Einstein curvature tensor in the L bar L direction, or rho, I think, in the standard notation for whoever that means anything. So here we find this property for this quantity that I'm integrating to give me the Hawking energy. Notice, of course, because the metric is just the round metric for the null cone, the area form for any cross-section is just omega squared times the area form on a round S2. So if we calculate the Hawking energy, what you see, let me go to a new board. So the Hawking energy then, oh wait, I've already given it a title. I don't know why I did that twice. Okay, so the Hawking energy is then what exactly? Well, we've got the area of sigma, which is the integral of omega squared over the round metric. This is being divided by 16 pi. And then we're integrating k minus 1/4 h inner product h. That's 2m over omega cubed, omega squared d sigma. All right, and we can just simplify that a little bit. This is exactly m, the square root of the integral of omega squared, the area form of a 2-sphere weighted by the total area 4 pi, and then the integral 1 over omega d sigma over 4 pi again. And what we just immediately notice from this is that this is always bigger than or equal to m by Jensen's inequality. Moreover, we will get the equality if and only if omega is constant. So just think about what that means in Schwarzschild. It means I'm looking at cross-sections with constant time slices of the null hypersurface. So you can recognize those constant slices in time as rest frames, i.e. sigma is a rest frame cross-section, if you like. All right, so we can see that this energy is always bigger than or equal to mass, and only equals mass when there's a notion of rest frame available. But now let's use the constant Gauss curvature cross-sections. Notice that if I have a cross-section that's got constant Gauss curvature, well, in Minkowski space, remember what that was. You took a null cone of a point, you took a hyperplane and you boosted it. That's what gave you that cross-section. Now let's go to Schwarzschild. We know at least far away from the black hole, Schwarzschild looks like Minkowski. And I can calculate these cross sections because I know what my function omega is. I can calculate the Hawking energy for these. All right, so what do we get? Well, we get 1 over, I forgot here, my apologies. You probably noticed a mismatch of constants. There should be a 1 over 4 pi here. Sorry about that. That's where we got the correct 4 pi's under those area forms. So if I calculate this, it's going to be 1 over 4 pi. Well, I now have a constant curvature, Gauss curvature cross-section. If we go back to the null cone of a point, it means that the integral of my omega squared, this is going to yield precisely 4 pi. Because it's just an isometry of the round sphere. So we know this is going to be 4 pi. And then we have 2m over omega v times the area form on a 2-sphere. So just writing this out again, we get 4 pi cancels with 4 pi. This is going to give me m. And then I have the integral of whatever the inverse, just the inverse of this. Here we had a factor of r0 squared. That's going to cancel the r0 that comes from here. So what we end up taking an integral of is exactly this quantity, d sigma. And that, the integral over here will vanish because when you flip the antipodal symmetry, here will give you a negative sign, which must therefore cancel. This is going to give you exactly this quantity. And maybe you recognize that. That is exactly the energy of a particle in special relativity that's been boosted with velocity v. So what these constant Gauss curvature cross-sections are telling us far away is we're measuring exactly the energy of the black hole when we are a reference frame that's boosted relative to the black hole. All right, so i.e., with relative velocity v. All right, so that's at least the motivation I can give you for why we think of this as an energy. There are others, but let me save those for a later day. Okay, so this also allows me to motivate the notion of total mass. I think it's just one n. Total Bondi-Troutman mass. All right, how are we doing? Any questions so far? So that's why we think of the Hawking energy as an energy. Because we imagine for null hypersurfaces in a asymptotically flat spacetime, the null cone will basically approximate to highest order the Schwarzschild null cone, and then I'm going to use basically this Hawking energy for leaves of the foliation that become round as a measure of total energy inside the null cone. Okay, so what we do in general is we take a foliation for a null cone that's geodesic. Okay, so L bar here is just an affine vector field. Okay, geodesic foliation. And the procedure is you specify then decay conditions on the data on this foliation so that it matches Schwarzschild or Minkowski to highest order. All right, so for sigma s geodesic foliation, we impose decay. And here's where I'm fluffing the exact definition to highest order. No, this is now in general. So in general, how do we define the mass of a null cone? You take a null cone, you look at a geodesic foliation, and you say that your null cone is asymptotically flat if the data to highest order agrees with a foliation of Minkowski. Okay, so to highest order, and so I'll lead you to Marsaria's paper, 2015. There's only one of them, so rather than giving the title for exact definitions of what I mean by these decay conditions. All right, so we need these decay conditions in order to know that the Hawking energy is going to be finite. All right, and then we need to study different foliations of omega. So I will say a foliation is asymptotically geodesic if the parameter defining the cross-sections is related to the affine background by some function phi. And something that just decays sufficiently fast. All right, so asymptotically geodesic foliations will be related to the background foliation just by the rescaling of the parameter. And when we assume this condition on omega, we get an interesting relationship to the metrics at infinity. So what we find is if I look now at 1 over s star squared of these metrics along such a asymptotically geodesic foliation, they will now tend to exactly that square in phi times some metric on S2. And we think of this as a metric at infinity. Okay, so with these conditions specified, if you look at these metrics as S star goes to infinity, you get exactly a conformal rescaling of what you would have had you done this for the background foliation. And then what we can use is the uniformization theorem to say okay, so by the uniformization theorem, just choose the appropriate geodesic rescaling, so make this exactly equal to 0. Choose the right factor so that this metric becomes round at infinity. Okay, so by the uniformization theorem, we can choose gamma infinity is just a round sphere. All right? So we can make that choice just by choosing the appropriate function phi. All right, so if I've made then a background foliation choice that goes to the round sphere at infinity, then I have finally the Bondi energy. So for any rescaling then by this omega that I've given before, we define the Bondi-Troutman energy, which will now depend on the choice of V, to be exactly the limit as S star goes to infinity of the Hawking energy of sigma S star. All right? So I can choose the background to become round, and then all the energies will be related just by taking geodesic foliations or asymptotically geodesic foliations that hit these graph functions that we saw that I'm erasing right now. All right. And from that then, we define mass just to be the infimum over all V. Okay, so and this is the Bondi-Troutman mass of omega. Okay, so that's how we get hold of a mass for omega. Okay, so let me quickly describe what a marginally out of trap surface is, and then we can prove finally the null Penrose conjecture in shear free vacuum. All right, any questions so far? All right. Sorry? Say again? You're going to have to dig into some interesting Shane Yao proofs of positive Bondi mass that I'm definitely not going to go in. But you can use.
By using the Hawking mass definition, it's not easy to see this derivative.
No, not that I know of, no. I mean, we'll see it for a special case in a little while, but in general, I haven't seen a proof yet, no. I mean, you lean on the fact, I guess, that the Hawking energy will produce all of the natural definitions of Bondi mass that you already have. But yeah, of course, directly from that, you need to dig into the equations a little deeper. And we'll be able to do that in shear free vacuum, but in general, I haven't seen a way. Okay, so what is the null Penrose conjecture? Now that we know what the total mass is, I need to tell you what the black hole is. Okay, so for that, I'll just quote Penrose. All right, so Penrose, and a good reference for this that I like is a book by Brad O'Neill, Semi-Riemannian Geometry. Of course, you can go to the paper. This warms you up a little bit though. And this is chapter 14. Okay, so this is the Singularity Theorem of Penrose. So what Penrose shows in our context is if you choose a two-sphere in your null cone that satisfies the fact that the inner product with mean curvature in itself is negative, we can find a incomplete null geodesic. Excuse me, an inextendable. Geodesic, and this is what we recognize as the black hole. But he shows a little bit more. All right, so on the way to this, he shows that for an event horizon, H, the future with a specific definition of a sigma that satisfies this is in fact compact or trapped. From null infinity by this event horizon. There should be a T. Okay? So what I'll call a black hole is kind of the boundary of all such surfaces. Okay, so the way that we think of the boundary of a black hole then is the and that means a surface where H inner product H vanishes. Okay, and this we call a MOT. And this is what's going to play the role of our black hole. Okay, so notice, if these sigmas with negative inner product of mean curvature lies behind the event horizon, because we've shown that a null cone has increasing area as you flow to the past, we see then that this forces the area of a MOT to be no larger than the intersection of the event horizon with our null cone, and what we conjectured this to be is smaller than the Bondi-Troutman mass. So that's what we want to show. All right, so you need a local definition of a black hole. We use a MOTS to be that definition, and we want to show that that's bounded above by the Troutman-Bondi mass. Okay, so from now we have something concrete geometrically to lean on as the definition of a black hole. This wasn't well defined because we didn't necessarily know exactly where it was, et cetera, et cetera. So this is really what we're trying to show. All right, so let's do that for a special case. And in order to do that, I'm going to need a quick lemma. So lemma for, so I've told you what tau was. So let me define something called rho. All right, and it's just something I use because it's got really nice propagation properties. So it's the first two terms that we need in the Hawking energy plus a divergence. So notice we can also give the Hawking energy as the integral of this rho. And it has an interesting propagation formula, which I will not prove. Tau is the connection one form that you have. Do you remember from the from this basis? Yeah. So tau was 1/2 dxi L minus L plus. Yes, that's right. So now I'm finally going back to that gauge-free basis at the beginning. And I do it because it has really nice propagation. So rho in this definition has the following formula. So let me actually put the three. Okay, so if you take its derivative, and this is along any foliation, not necessarily geodesic, you get 1/2 trace chi bar, 1/2 H inner product H. You get trace free part chi minus GL minus L minus. We get the square of tau, 1/2 GL minus L plus, and close bracket, and then everything else integrates to 0. Let's see, enough parentheses, yes. Minus 2 divergence trace chi bar. And then finally, plus the divergence of GL minus. What I mean by that is just the one form you get on a two-sphere when you plug in the L minus direction. Okay, so I know that's a mess, but notice what's going to happen if I'm in vacuum trace-free. Everything on the right except the tau squared will vanish. And we also get an interesting propagation equation for tau, negative trace chi bar tau I. And then everything else will vanish when we set it in vacuum. So this is trace chi bar chi hat minus plus u, trace chi bar GL minus xi, and then plus xi, this quantity. L minus close bracket. Okay, so the proof of this is just study those structure equations.
This is independent of the applied problem.
Yeah, that's right. Yeah, this is true in general. That's correct, yeah. Okay, so the reason I gave you this mess is because I need it. So for the theorem, assume omega is in vacuum. And it's in trace-free. And then assume I have a MOTS. Then we have that the area of the MOTS over 16 pi is smaller than the Troutman-Bondi mass. So why is this true? Well, as I've mentioned already, if you look at least tau and rho's propagation, everything vanishes except, well, for tau, you're just going to get these two pieces. Everything else goes away. So this, you can use the propagation equation for trace chi-bar to get exactly an expression of trace chi-bar along an affine foliation. And then you can solve for tau using this equation, and then you can solve for rho. Okay, so it's just giving us a bunch of geodesics when you assume vacuum trace-free. And then you can claim immediately what trace chi-bar is. It's just trace chi-bar 0. So here, let's just go to a geodesic foliation. You get this just from the propagation equations. You're just solving ODEs. There's nothing to it beyond that. The metric is just going to be an S over 2 trace chi-bar 0 plus 1 squared times the initial. Okay, so this is the metric on the MOTS. And notice from this that the area form is exactly S over 2 trace chi-bar 0 plus 1 squared det gamma 0. Finally, just from our lemma, you see that tau is exactly S over 2 trace chi-bar 0 plus 1 to the negative 2, and then tau on the MOTS. And then finally, we need rho. And rho is going to be exactly S over 2 trace chi-bar 0 plus 1, negative 3 power here, rho 0 plus 1/3 tau 0 squared, and here you just get a 1 minus S over 2 trace chi-bar 0 plus 1 to the negative 3. So that's all we need to plug into our formula. Okay, so quick observation here. Notice that rho 0, if I'm on a MOTS, is exactly the Gauss curvature plus the divergence of tau 0, because the mean curvature contribution is gone now. Okay, so all I need to do is plug this into the Hawking energy and then see if we can analyze what we get. So this is an answer to your question, at least in this case. You can actually study the limit exactly. Okay, so what is the Hawking energy? Well, E sub h of sigma s is 1 over 4 pi, and we're integrating, and I gave you the area form. It's S over 2 trace chi-bar 0 plus 1 squared, and the area form over the MOTS. That's divided by 16 pi, and then we integrate. You get, once again, trace chi-bar 0 plus 1 to the minus 1. All right, so why is that? I'm integrating rho to get the Hawking energy. Remember, Hawking energy is 1 over 4 pi, area over 16 pi, the integral of rho. The integral of rho provides a S over 2 trace chi-bar 0 plus 1 to the negative 3, and then the area form provides a square. Okay, so this is going to be the only decay in S, and then we get the Gauss curvature on the MOTS plus the divergence of tau on the MOTS plus 1/3 tau squared on the MOTS, and everything else is to order. Let's see, I think it was minus 3, yes. dA0. So if I take a limit as S goes to infinity, let me start a new board. You see exactly where the Hawking energy goes. For this flow. All right, so we see the Hawking energy goes to 1 over 4 pi. We have the integral of trace chi-bar 0 squared dA0 over 16 pi the integral trace chi bar 0 to the negative 1. The halves cancelled, right? We had a half, but here we had a half. Those go away, and we're left k0 plus divergence tau 0 plus 1/3 tau 0 squared dA0. Okay, so this is the limit you will get along an arbitrary geodesic foliation. So what distinguishes one geodesic foliation from another? The trace chi bar 0 choice that you made initially. If I shoot at a different speed, I will get a different limit. Okay? So I would like to know what happens when they become round, right? So how do I know which ones become round? Well, notice I need to weigh the metric by s squared along my foliation to see where this goes. This is exactly s over 2 trace chi bar 0 plus 1 squared times the metric on the mots. And this goes to 1/4 trace chi bar 0, the metric on the mots. Now, by uniformization, I can decompose the metric on the mots as some square of a positive function times the round metric. Now there's a gauge freedom in the choice of round metric, and that's going to be because of the different ways that I can choose k to be 1. So let me just indicate that I've gone to one of them by putting this subindex v. Okay? So if I can decompose the metric on the mots in this way, my foliation is round if I choose trace chi bar 0 to be 2 over exactly this function. All right. And then what do I get for my Hawking energy? That means that my Troutman Bondi mass, which will depend on this decomposition at the mots, is given by 1 over 4 pi. And notice this is exactly, if I put one of the fourths upstairs, this is 4 pi divided by 4 pi. So I'm just integrating trace inverse, so that's psi v over 2. Now notice if I do make this decomposition as well, then what's the Gauss curvature of the mots? It's exactly 1 over psi squared 1 minus, and this is just the Laplace-Beltrami operator of this round metric. Okay, so I can replace this for the Gauss curvature. All right, and remember, I've got a divergence on the mots, and divergence operator is conformally invariant, so that will change into the divergence on a round S2 as long as I provide the 1 over psi squared. And the same is the case for the last term, where I've taken a square, and then this is integrated over this guy. Enough parentheses? Yes. Okay, so notice what I get from the area form will cancel everything inside, and then I can perform an integration by parts, and I end up with bringing the 2 out, 1 over 8 pi. So all of the psi squareds and 1 over psi squareds will cancel. Then I'll hit psi here with 1, and then I can perform an integration by parts. All right, and I'll also do an integration by parts over there on the last 2 terms, and that will be rewritten then as 1/3 tau 0 psi minus the gradient of psi. Okay? Now I'll leave it as an exercise, but you can show that this, just by simple variational calculus exercise, this is always bigger than -3/4. All right, so we see, finally, this is 1/8 pi, the integral psi phi plus 1/4 squared, like this. And now I'm going to use an optimal embedding theorem due to Beckner to show you that that quantity is always bigger than or equal to the area square rooted of the mods over 16 pi. Okay, so Beckner you have an embedding of any L cube for q between 2 and infinity into H1, and here I'm just choosing S2 to have area 1, and then you can show that q minus 2/2.
I guess you should reverse the arrow.
Say again?
You should reverse the arrow.
Yes, thank you. Wait. Let me write, yeah, I think you're right. Let's see. So u squared is bigger than or equal to LQ squared. Let's see. So if I'm in H1, yes. Anyway, this is the inequality I want. My brain is shutting down. Okay. So we can. Yeah, this is, excuse me, yeah, thank you, this is L2. Yeah, sorry, yeah. What's the norm? L2. Okay, so we choose Q to be 4, and we choose U squared to be C, which we know is positive. And then what you'll see here is you'll get your 4 cancel. This will be precisely 1/8 pi. Excuse me. Yeah, so this is the area. This is going to be exactly plus. What happens is you have to move in a 4 pi into the integral. So we're left here with a half plus u L2 squared. And this is bigger than or equal to what we want. Okay, so this is bigger than or equal to 1/2 the integral u to the 4 d sigma over 4 pi to respect the area to the 1/2. And what you'll notice is this is exactly the square root sigma 0 over 16 pi. And there's no dependence on v on the left. So also true for the infimum over v. And that's what we wanted to prove. And this is a theorem due to Johannes Sauter in 2008. Okay, thank you.
So this applies to a Robinson problem.
Yes, shear-free vacuum. Yep.
Yeah. So when equality holds, we know it's
I guess, oh, yes, you do. So I wanted to put the case, you know that it's exactly the Schwarzschild data. Yeah, so if you have equality, the inequality here will force tau to be identically 0 when you get equality here. I can't, wait.
That's just completely square, right? That inequality just...
Yeah, in some clever way. The argument comes through here. As soon as you have equality, it'll force everything that we made inequalities, and it'll force the initial Gauss curvature to be round. It'll force tau to be 0. You basically just rebuild all the data that you have for Schwarzschild. and then you can show that any foliation is independent. You can basically just show all the geometry of the null cone is exactly the same as for Schwarzschild.
But that, that corresponds to tau equals 0?
No, I think you might have to go around. K has to be 1. You're in vacuum, so you're shear free. So if K is 1, then you'll have something on the mean curvature, and you can run through all the ODEs and show that the data matches.
It's hard to write down the discrepancy as it's just a quantity, and you immediately see that the equality holds space.
The difficulty is knowing the discrepancy, I guess, between this and this. I don't know. I haven't seen it. No. I mean, there are a couple of places where you can definitely do it. Like you said here, you can complete the square probably. I don't know how to characterize the discrepancy between these. Maybe in spherical harmonics you could do it, because that's how I think he proved Beckner's inequality. But I haven't seen an explicit, nice discrepancy formula. Due to Alice Turing? Yeah,
So we know that equality holds even only if
Schwarzschild.
omega is null hypothesis Schwarzschild.
Yes. That's right.
Here, doesn't only show the equality for 1 to b, right? How does solve
Say that again? For 1V? So, I mean, what I said was there was an ambiguity with the choice of V in the way that I decomposed the metric and the mods. So this inequality holds for each one of those choices of V. So you can take an infimum. So you've actually shown that it's actually a lower bound for the bonding mass, not just an energy. Thank you.
There's no limit, we will